All right, everybody, I'm back at it, and I just looked at this data and I thought to myself, wait a minute. The formula that we were looking at in this document here was suggesting that sea level was at 320 meters and that we were going to do below the plane at below or equal to 320 and above 320. That's yay hooray. It's all fine and good, except do you notice that in our data this is going from 217.75 to 241, so anything below 320 is well below sea level, and so there's nothing above 320 to be above sea level. If 320 was at sea level, then everything in this map is below sea level. And I don't know that that's true for Manitoba, so I'm kind of confused, but I went to chat with this problem and I said, let's throw out everything that we've been told. And I asked it, let's see what I said. I said, all right, let's try a different approach. If you were going to create a sea level mask with this data, what would you do? Forget the instructions they gave me. Look at this image in the dating, the Cooks Creek LIDAR clip layer, and let's do it your way. It's a great approach. Instead of following rigid instructions, let's strategically create a sea level mask using a reliable and efficient method. So it suggests that we create a binary mask, which is nice, but the problem is it still used 320. Anything under 320 would be water, and anything over would be land. And then I said to it, after it gave me the whole procedure, I said, before I do this, do you notice that the range of colors in this layer band is 217 on the bottom to 241 on the top? Will that affect everything? He goes, yes, that range is a big deal because it means your DM does not have elevations reaching 320 meters. So there's no pixels in the DM that'll satisfy less than or equal to 320. So that isn't useful. So it suggests we do something. So you have to really prompt your AI well and think through these things. It doesn't do things for you. You're having a dialogue. It's very Socratic. All right, so what we're going to do, it says we should do a histogram, and then we'll see the real distribution of elevation, and then we'll find out what a good threshold is. So to do a histogram, we're going to open the layer properties. So go down here to properties, and we'll go to histogram, and I guess we apply it. I don't see anything though. That didn't do anything. Why? Compute histogram. I guess you have to compute it. All right, so the histogram says most of the values are in the 200 and whatever that is. And then there's very few values that are up there. So there's very few high values over there. And there's a few of them down in here. So the min is 217. The max is 241. We knew that. Okay, and then I guess I should ask chat. So let's give chat a chance to look at this data. Here's the histogram for you. And we're going to put that in. See what it says. Right. Most of them cluster 222. Choose a realistic threshold. The low threshold will cover the majority of the terrain. Highlight the lower lying flood-prone areas. If you want to mask areas below 225 as water, then do that. And then low equals water, and 0 equals land. Stricter flood level, only highlighting the lowest points. You could use 220. Run the updated raster calculator. Yeah, well, let's try that then. So we will go in, having looked at the histogram, and we will then once again use the raster calculator, and we will once again select the Cook's Creek LIDAR clip, and we will use an expression which is Cook's Creek LIDAR clip. I don't know what this @1 means, but that's going to be what it does. And then let's see if even this works or if it crashes.
I didn't clean all of my toys.
So
This is not a code. 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 This is not a code.
it worked. It worked. All right. So that one worked. And we're seeing in black and white then that in the calculated, 1 seems to be the highest, and then there's the flooding areas down there. And if I look at, let's turn off the soil, and let's also make this transparent. But really, you know what? This is crazy what I'm doing, because the LIDAR should be based on whatever is here at the entrance to the water, right? So when we go up in here, somewhere down here at the lake margin, particularly if I were to get down in here, maybe I should now bring the transparency back up. We should know what the lowest level, because I'm being really stupid. Sea level is whatever the lowest level is, because otherwise it's bouncing off the water because there is water right there. So I've been very foolish, and I should tell ChatGPT that. Right. Now the transparency is total. Let me bring it back up. I should say chat, I think we are being foolish. Map shows a big lake at the top of our DEM. Wouldn't that be sea level from a water perspective, regardless of how the terrain really is in relation to the sea? And wouldn't that imply that the lowest value of 217.757 is what we would want to use as the baseline for water? When I need to give it a picture. And then check its logic. And it says, you're absolutely right. It's a natural reference for sea level. In this context, we should use that as the baseline. Therefore, new plan, use that as sea level. Instead of filtering everything below 225, mark them as existing water. Make sure that's the level.
And the biggest poison, that's guard dogs. That's
what did we have originally? We had could we now modify the original expression on the tutorial to reflect this value and the new name of the clip? Remember, we had
and the guards dogs attack you. There's another guard dog.
So this should be it. Okay, why do you keep adding @1 to the name? And that student is always asking how it handles raster bands. @1 refers to band 1 of the raster. Since there's only one band, it appends @1 to indicate band 1. If they have multiple bands, first band might be elevation. Oh, when there's red, green, and blue bands, you might see raster layer 2, maybe slope, maybe aspect. I had no idea. If you need it, if it has @1 in the raster bands list, you must choose one. If it only shows that, and omit it. Okay, so we're going to use this then. Okay, this is great. So then once again, we're going to use this clip. We're going to go to our raster calculator that was giving us so much trouble before. We're going to use this clipped Cooks Creek LIDAR clip. And use that. We're going to say OK. The expression is going to be that. And now we're going to run it. And this time, that expression didn't work. We're not collectively generated. Oh lordy. Alright, what's wrong? Maybe we need that one. Let's try it with that one. Maybe because it says band 1, it needs it. Let's hope it works. Otherwise, there's something wrong with the expression. But we're learning all the time. The moment of truth is upon us. Ah, it worked.
Yeah,
It
duh.
worked. What do you mean, yeah, duh? What do you know about it?
Yeah, duh.
Yeah, duh. So I guess it needed the @1. And so now, yeah, duh. Take that off.
Yeah, duh.
Yeah, yeah, duh.
Duh.
So that is the
Yeah,
sea level
yeah,
down there, and everything else above it is not sea level. And if we compare that to the calculated where we just used that, well, that doesn't do anything.
Yeah, duh.
Yeah, haha.
Yeah, duh.
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 Okay, now.
Yeah, duh.
Thank you, buddy.
Yeah, duh.
Right, well, it works, but it comes out all black. So I got to ask ChatGPT about that because the other one did not end up all black. So this is weird. Now it all is
I think the black is the void.
it's the void, yeah. Hum.
If I save the toys and I'm really sick of it,
Something went wrong in the rest of the blast magnet, all values are 1. We set all pixels to 1 and land instead of correctly differentiating. The elevation comparison wasn't correctly applied. There's a data type mismatch. Try reversing the logic. Okay, try that. So water is below 217 and land is above. And then see what it does. And so we'll go back, erase this. We will select this clip. We'll go to the raster calculator. We will select the LIDAR clip. We will put in the expression and we will run it. Wrong or missing parameter values. Oh, it's acting like it doesn't have anything. I thought I selected this. There, okay. Let's try that. Let's see what happens. And this time, still black. Although it says that there's something. We go to this and go to the histogram, calculate the histogram. There ain't nothing. Okay. Oh, that's not working. So if we go in here and do what it originally suggested, which is
time for no guardians here.
out of here and just say,
I'll get this material.
the lowest value
this material
would be water, and pixels above would be land. Try that
This material.
once again.
I'll get this material. This material is so strong. It's wood. Keep mommy out. Snap. Let's get
So it isn't working, so I'm going to raise this up to 225 like we'd seen before, and at least see if there's any logic that makes sense in this. And so here 225 is that's where sea level would be, although it's really odd because it looks backwards, and I guess when you look at this, yeah, the one is white and the lowest is 0. That doesn't make any sense. So it probably should be, if you compute the histogram, very much. If we were to turn the symbology around and invert the colors, then you'd see something that's more like what you would expect. And when you look at the values in here, this is 0 and this is 1, using a cutoff threshold. When you look at this, you see that this is, click on it, this white is 239 and this is 218, 218, 218. So we're trying to make a plane that will rise, I believe, is the intent with that, and to show that flooding would occur all the way up to a certain area if it rose above a certain height, that being 225. And then we have this sheet of flood, so everything under that would be flooding. So you set where you think the flood levels could rise to, and then see what buildings and what objects are above that. So what he's doing here, he says that he's showing the DEM, the newly made mask. Lightness corresponding elevation higher is lighter, and the mask shows the cutoff as black below 320 and white is above it. So Here's the sample area with flood masking applied to it by being overlain on top of the BEM with buildings placed around it. Area of higher risk if the water level reaches the elevation of the mask. And so that's, I guess, what you're trying to do is see, do these buildings reach the level of the mask with the buildings? And since we don't have any buildings in our data, then we can't really do that. So I probably should not have used this area here. I should have been down here in Winnipeg with my LIDAR map, because I have nothing. When I look at my Manitoba, we'll see if it draws anything.
Tough material.
It's probably not showing up because it's underneath the layer. So I need to find, I don't know what the Google Hybrid is there. So maybe it's just not yet come in. Oh, now it's beginning to come in. Goodness gracious, there it comes. It's a huge data set. But I don't think they have any buildings for, if I turn off the hybrid, maybe they do. Let's see, yes, indeed they do. Okay, so there are some buildings in here, so we can do the exercise. Probably should put this over the map. Bring this underneath. Now, as we go in, I should probably also change the color so you can really see these well. Aha, so these are all the houses that would be flooded at that level. And that means that the clip that we do for this needs to be what we have the LIDAR for. So this is beginning to work. So there's that. All those houses are going to be flooded out. Let's go up to Manitoba. Let's do the vector mask. So we go into vector clip, extract clip by extent. Manitoba, the extent is this, and clip features to extent, and then run it. Don't know what the snow spatial index exists thing is about, but looks like we got the little thing. Here's the extracted. That means we can undo Manitoba, but we do need to make this extracted if it worked. Let's make it obvious. There we go. Okay. Much smaller data set, but look at that. Those are all the buildings that are going to be severely impacted at that flood height. And so you can keep calculating this. So I'm going to put this, make this extracted buildings. Buildings, oops. Or Creek flood. But this calculation then is using different values for the flood. So if, for example, we wanted to run it again and we wanted to say, using the raster calculator, we wanted to say, great, well, let's for that. If we do Cooks Creek and it floods, and the expression is not 217, but let's say that it got as high as 230. And then you can run this and see what it's going to look like for 230. Right, so all of these houses, if it gets up to 230, all of these houses are toast, and only these ones here on the very margins are going to be okay. Everybody else is going to be completely flooded, as you can see. So not.
Where is the flood on everybody else?
This would be the white would be where the flood is. All their houses, which are these little yellow dots, and I can change their color so you can see. If I change the color, let's say we change them to red.
What about brown?
Could do, but see, those all those people are going to be underwater. So they're not happy campers at that level.
And where are the houses?
Those are the houses, all those little red dots. And if they're in the white area, then they're flooded under. Because I didn't flip it around.
And the people are not in the white area yet.
Right, and this is at 217. I'm sorry, 225. This is where the flood waters would move up to, right up into there. So they wouldn't be happy. So that's how you use a clipping mask to show what would be tragic. So this is 225.
Daddy,
yeah.
Daddy, where is the Daddy?
Yeah. Hold on, this is 225, so I need to rename this. Rename it. 225 meter flood.
Daddy.
And then the other one is this one.
Daddy, where is the void? Where people fall down and they never come back? Where's the void?
This is 230. So here, what I'm going to do for this is,
What?
I'm going to click on this. I'm going to say invert colors, like that. I'm going to apply. And now that is where people are safe, and this is where they get drowned if it's at 2.
The black is the drown?
Yeah, the black is the drowned.
The black is the drown? Where are the people?
They're not there.
Where are they?
No, they're not. This is just a map. It's not real people.
Where are the map people? Where are the map people?
So there's possible now to do something interesting. We can say, using this LIDAR data, what we can say now is that while everybody here seems to be safe at 217, and it doesn't appear that anybody built any houses down here, and I guess that's because they're afraid of floods. They're like the closest to it are these people here. So the people who are the most vulnerable. No.
Can you please stop?
So this looks like
this headphone stop.
this is the floodplain.
Yes.
There's a home there.
Almost done. I need a few seconds. This headphone doesn't work. It works.
All right, so what that means is that something like this farm here is going to be in trouble, as are these farms down there, and nobody's built anything too close to this river, which would overflow. And so if we can actually get from this map where this river is, you can see this house here is fairly vulnerable. These people, well, they're on the dock, right? So when you look at the actual LIDAR clip and you see these values here, you note that that house is sitting at 221.03, and the river, which we can't really see unless we make this somewhat transparent. So let's go up and let's put a transparency value like 69% and apply it. See, but yeah, there we can see it. So right here is 218, and here the dock is 218.05, 0.07. The shoreline is 218.460. I mean, a meter is 6 feet. So since we're doing meters, you've got to think about like the water, which isn't even uniform around here for some reason. I guess that's just the bounce that you get. But it's like the highest values, 218.132. I think if the dock goes, then the house is going to have trouble. Like their lawn here is at 220, this area here is at 220.4, and then over here is that. So they're right on the river. So their farm 220.44, 218 is down here in this marshy area, but it looks like their lawn is a bit above 220. Similarly, if we look through and see some of these other properties, like the road here is 221. This house is 221. I'm looking over here on the right. The margin here, 218 down in there, but where their farm is 220.9, 220.7. So 220 is probably a pretty reliable indicator of where flooding would start to impact people. So let's try it again, and this time let's grab this. This is getting fun now. And go to our raster calculator and take that input of the LIDAR, clip, have the expression be 220, and and maybe instead of having to invert all the time, let's just make it greater than or equal, and then the colors will work out. So we want to have it be 220 where you're safe, and anything under 220 or equal to, so greater than 220 it should say, not equal to. If you're greater than 220, you're safe, and if you're not safe. Let's try it like that. And say calculate. Okay, so it's run. And now we can see that everything white is where it's safe, and where it's not white, you're at 220 and you're going under. And so that house there is safe. And again, I've got to make this region, if we're really going to look at it, I've got to make it, first of all, I've got to change this to calculated. So I need to rename this and call it calculated 220 flood. Okay. And our extracted buildings go over there, and yeah, you begin to see that a flood of 220 is not going to have a big impact. People are going to do okay right there, but there's going to be some people who are vulnerable. So nobody's built anything where it's less than 220. So you don't see any red over the black, because this is very binary. The water level is 220. But there's all sorts of homes that could be impacted if it gets any taller. So 1 meter would be 3 feet, sorry. And that's unlikely to happen 3 feet. But what if it just rose by 1.5 feet? Like, who here would be damaged if it went by 1.5 feet? So let's go again and see 1.5 feet, which is, certainly reasonable that could happen. Let's do another calculation and go take that clip and say if it is greater than, you're safe if you're greater than now, greater than, you're safe if you're greater than 220.5, a half a meter, and run that. And it's run, and let's see what a 1.5 feet does to some people. We have anybody who's in harm's way. They can all accomplish. Oh, there you go. There's our first victim right there. So this would be calculated 220.5. And our first victim, as we can see when we go to the transparency, go to 50% about. Yeah, that house there goes under. A lot of this farmland goes under. These people are still okay. It's also, let's turn it off and then turn it on. So we're also looking at the LIDAR clip. So we're looking at a lot of this place now. If we go to the calculated, but it's very interesting to see where people actually build because they use these models for that. Let's bring the opacity down just a little bit more. Come in here. So the flood is obviously going to cover this entire floodplain up in there on the banks of the river. And then these people here are going to lose all around them. Yeah, they're going to lose these parts of their farms there. They might keep a bit of the main house there. That's underwater. They'd still be able to get out. They can get out this door. It'll be marshy and wet if it's a foot and a half above. And they'll try to make their way up this path to their neighbors over here. And these people will just barely avoid it. But this neighbor down here can't get to the road. The road's going to be submerged to this dip down there. These people are going to be isolated. They can't get out. They'll be safe. They'll be stuck. And that's going to be the most dicey region over there. These people are inundated and isolated on a little island. And if it goes up another another foot, then they're drowned out. That's the power of this kind of map, which is pretty cool. So what does the exercise ask of us? It shows us who's been cut off and the flooding mask. Area of higher risk inundation, high risk zone. It would be informed with a sensible color and labeling scheme, so we want to raster data can be rendered in different colored palettes. Great, and shifted and bands can be colored differently. Open its properties, transparency control there. Unlike for a vector layer, vector-based data for the buildings, you can recolor, and then tweaks are done in that menu. So just telling you about labeling layers, and then you can do a symbol. Now the 3D viewer. So we can show this from an aerial view and tell it to use the DEM as elevation and use 1 to 14. Okay, so let's do that. Let's go back in here and let's use layer, so view 3D map views, do a new 3D map view. And show this. Now we haven't yet got any elevation information, so we have to go here and tell it that we want to make it a DEM raster layer. We need to tell it what we're going to use, and we use the DEM clipped LIDAR. The LIDAR clip would be the one to use. And then we should begin to see some information, except it's not exaggerated. So once again, you'd have to go in here and tell it the vertical scale, as he says, you can make it up to 5 maybe. See what that does. Yeah, almost.
I wanna look at something. You can work, but don't. Can you help me make
I'm almost done.
See, it's getting to be 10. You don't stop. You don't
Yeah,
have to
dude.
stop. You can go to the other room.
No, I'm done. I'm done.
No, Tia. I mean,
I'm
you
done,
have to
and
stop
I'm
right
recording
now.
right now, and I will stop right now.
Because
All right,
it's
so
about 10. You don't stop. You don't have to stop. You don't have to stop. Go to the other room. Let me and I wind down. It's 10. Almost done.
all right. Well, that's what they want us to do. It's not really showing up tremendously through here, but we'll stop right there.